Most students can spot benzene and tell me it's aromatic, but the minute a charge shows up, or a heteroatom, or an 8-membered ring, everything falls apart. In the next few minutes, I'll give you a system where you can classify any ring as aromatic, antiaromatic, or non-aromatic without resorting to memorization. If aromaticity feels slippery, you're not alone. When there are special rings, heteroatoms, charges involved, it all starts to feel like a maze. In this video, we'll build the entire system from scratch. And by the end, you can predict a molecule's aromaticity with complete confidence. Before we get too deep into all sorts of examples and rules, let's define what aromaticity even means. Sadly, it does not have anything to do with the molecule's fragrance. One thing we have to internalize is that aromaticity is ultimately a measure of stability and therefore reactivity. Aromatic molecules are more stable than we'd otherwise expect and therefore less reactive. Anti-aromatic molecules are less stable than we'd otherwise expect and extremely reactive. And non-aromatic molecules have normal stability and react just like we'd expect any other molecule to react. So aromaticity isn't about smell, it's a reactivity shortcut. Everything we do in the next few minutes is about predicting the stability of a given molecule. I'm going to start drawing molecules and labeling them with their categorization, and we will derive the rules along the way. To start out, let's compare benzene, 1,3,5-hexatriene, and 1,3-cyclohexadiene. Benzene is our prototypical aromatic molecule, but 1,3,5-hexatriene and 1,3-cyclohexadiene are non-aromatic molecules. Their stability is as stable as we'd otherwise expect. So can you spot the difference between these molecules and help me predict some of the rules? Why is benzene aromatic but not 1,3,5-hexatriene? Why is benzene aromatic but not 1,3-cyclohexadiene? The first rule of aromaticity is a molecule must be cyclic in order to be aromatic. Acyclic molecules, no matter how similar they may look to aromatic molecules, will never be aromatic. Being cyclic is the first rule in our rules for aromaticity. For our next pattern, even if the molecule is cyclic, if there's even one sp3 hybridized atom in that ring, the molecule will be not conjugated and not fully aromatic. I'm going to call that rule number 3 in my list. We'll come back to rule number 2 in a minute. Aromaticity is a measure of stability. Fully conjugated molecules have a p orbital on every single atom, and all of those pi electrons are free to delocalize around the entire ring. It's that spreading out of electron density in the cyclic ring that imparts the extra stability to the aromatic molecules. If we have even one sp3 hybridized atom in a ring, we might be able to draw some resonance contributors, but we will not be able to draw resonance contributors that touch every atom in the ring. The molecule might be partially conjugated, but not fully conjugated. And if the electrons can't delocalize in a cyclic ring, the molecule is non-aromatic. Students often feel this rule but struggle to put it into words. So here it is clearly. Every atom in the ring must have a parallel p orbital all the way around the ring. That's all fully conjugated means. We should be able to draw one set of arrows to draw a resonance contributor that touches every single atom in the ring. If we can't make it to every single atom in the ring, the molecule is not conjugated and not aromatic. The next set of examples involve these 3 structures. Cyclobutadiene is our first example of an anti-aromatic molecule. Naphthalene is an aromatic molecule. Methylbenzene is an aromatic molecule. Here, we're going to be targeting rule number 4. Can you tell me what the difference is between these rings that allow the naphthalene and benzene to be aromatic, but cyclobutadiene to be anti-aromatic? In each of these cases, the molecule is cyclic. Naphthalene has the bond in the middle, but it does have a globally cyclic structure. All of these molecules are also fully conjugated. Even cyclobutadiene has p orbitals at every position. So why is cyclobutadiene anti-aromatic? And what changes but stays the same to allow naphthalene to be aromatic? It has to do with the number of pi electrons in the system. The rule at the end of the day that determines whether a molecule is aromatic or anti-aromatic is the number of pi electrons. It's perhaps the rule that causes the most stress for students. We have to be confident in our ability to count the number of pi electrons. And once we've counted the pi electrons, we apply that to the 4n+2 rule. Each pi bond contributes 2 electrons to the pi system, so benzene has 6 total pi electrons. The 2 pi bonds in cyclobutadiene give cyclobutadiene 4 total pi electrons. And the naphthalene system has 2, 4, 6, 8, 10 total pi electrons. The way the 4n+2 rule works, sometimes called Huckel's rule, is we set 4n+2 equal to the number of pi electrons. So for benzene, we would say 6 equals 4n+2, and then we solve for n. Subtract 2 from both sides gives us 4, divided by 4 gives us n equals 1 for benzene. For cyclobutadiene, we set 4n+2 equal to the 4 pi electrons. Subtract 2 gives us 2, and divide by 4 gives us n equals 1/2. And here's the key to Huckel's rule. When you solve for n in the Huckel's rule equation, if n is an integer, that molecule is aromatic. And if N is a fraction, that molecule is antiaromatic. If we've satisfied the first three criteria. In many ways, the first three criteria are gatekeeping criteria. We have to pass rules 1, 2, and 3 in order to apply rule number 4. As we saw in our other example, if we break any of the first 3 rules, we don't have to do the math. The molecule is just non-aromatic. It's only when we pass the first 3 rules that we can apply Huckel's rule to determine if the molecule is aromatic or antiaromatic. For naphthalene, 4n plus 2 equals 10. Subtract 2 gives us 8. Divided by 4 is n equals 2, an integer. Naphthalene is aromatic. Students sometimes get confused about methylbenzene, and this is where I want to remind us to step back. Aromaticity is ultimately a measure of stability, a measure of reactivity. If I throw some reagents at this molecule, is it going to react more like benzene, or is it going to more react like a regular double bond we saw back in alkene land? Hopefully, by stepping away from this molecule a little bit and just looking at it outside of all of these rules we've been deriving, this is just benzene with a substituent. It should react just like benzene with a substituent. So when we apply these rules, we only apply them to the cyclic ring. The decorations are just decoration. This is cyclic and fully conjugated. We still haven't quite gotten to rule number 2 yet. And it has 6 pi electrons. When we plug 6 pi electrons into Huckel's rule, minus 2 equals 4, divided by 4, n equals 1, methylbenzene is definitely aromatic. Students start to get a little nervous when charges start showing up in the molecule. But let me explain to you how they really actually make things a little bit simpler. The only effect the charge has on the molecule is adjusting the number of pi electrons in the system. That's it. When we look at the uncharged systems, what I want you to see is there's an sp3 hybridized carbon atom right in the middle of all of those double bonds. That means these molecules are not fully conjugated. We've broken one of the first 3 rules. We don't have to apply Huckel's rule. These molecules are non-aromatic. But let's see what happens when we have a charge in the molecule. The addition of the charge in the molecule means that these atoms can now participate in resonance, and that makes these molecules fully conjugated. They're certainly cyclic. We still haven't quite gotten to rule number 2 yet, but we can apply Huckel's rule to see if these are aromatic or antiaromatic. For the cyclopentadienyl cation, each pi bond contributes 2 electrons, and the carbocation is an empty p orbital contributing 0 electrons, so the cyclopentadienyl cation has 4 total pi electrons. When we solve for n, subtracting 2 gives us 2, divided by 4 gives us n equals 1/2. That means that cyclopentadienyl cation is antiaromatic. For the cyclopentadienyl anion, each pi bond contributes 2 electrons, and the negative charge means there's a lone pair there. That contributes 2 more electrons for a total of 6 pi electrons. Solving for n, 6 minus 2 is 4, divided by 4, n equals 1. The cyclopentadienyl anion is aromatic. All the charge does is change the sum total of pi electrons. That's it. Let's check the 7-atom ring version. By the way, if you want to get good at drawing different size rings, I have a video that I'll link to down below that walks you through the expert method for drawing 5, 6, and 7-atom rings. For the cycloheptatrienyl cation, each pi bond contributes 2 pi electrons, and the carbocation contributes 0, so there are 6 total pi electrons in this molecule. We've seen 6 electrons several times. When we solve for n, we get 1, so cycloheptatrienyl cation, yes, is aromatic. For the cycloheptatrienyl anion, the anion is a lone pair and contributes 2 electrons. Adding to the 6 total electrons gives us 8 pi electrons in this system. 8 minus 2 is 6, divided by 4 gives us n equals 3/2. That means that the cycloheptatrienyl anion is antiaromatic, which means it's less stable than we'd otherwise expect and very reactive. The last set of molecules that often trip students up is rings that have heteroatoms as part of the ring system. Students often freeze because the heteroatoms have lone pairs, but how do we know if those lone pairs are part of the pi system or not? We'll find that some of these lone pairs do contribute to the pi system, but other ones don't. How are we supposed to know the difference? Here's a simple approach. We only use a lone pair if it's involved with the resonance that makes the molecule fully conjugated. To be part of the pi system, the lone pair has to be in a p orbital that contributes to the resonance of the entire molecule. For pyridine, we do not need to use this lone pair to draw a resonance contributor that involves every atom in the ring. We can shift all the double bonds over just fine without needing to involve the lone pair. So pyridine is fully conjugated, but not because of the lone pair of electrons. The lone pair of electrons are not in a p orbital, they're in one of nitrogen's sp2 hybridized orbitals. These electrons therefore do not contribute to the pi system, and pyridine from the 3 pi bonds has 6 total pi electrons in its molecule. As we've seen before, that means n equals 1, and yes, pyridine is aromatic. For a molecule like furan, the oxygen has 2 lone pairs. Can any of them contribute to the pi system? Can both of them? Let's find out. I can draw a set of resonance arrows that touches every atom in the system. If I start with the oxygen lone pair, I can drop that down to form a pi bond, shift the double bond over, break the other double bond to put a lone pair negative charge on the final carbon. I couldn't have gotten to every atom in the ring without that lone pair on oxygen. So furan is fully conjugated because I used one of the lone pairs in resonance. But notice I only used one lone pair, not the other lone pair. As a general rule, a heteroatom can contribute at most one lone pair to the pi system. There's only one p orbital on oxygen, and only one lone pair can live in that p orbital, so only one lone pair gets to contribute to the pi system. This molecule is fully conjugated because of that lone pair, so that lone pair contributes to the pi system, along with the 4 others from the 2 alkenes, and that gives us 6 total pi electrons in furan. That means n equals 1 in Huckel's rule, and furan is also aromatic. Imidazole is the last example we'll do in this system. It has 2 nitrogens. Do either of them contribute electrons to the pi system? How many electrons contribute to the pi system? Here's a good mnemonic that can help you out. If the heteroatom is already involved in a pi bond of its own, the p orbital is already occupied forming that pi bond, and the lone pair cannot live in the p orbital and will not contribute to the pi system. If the heteroatom is connected to the ring through only single bonds, then the lone pair does live in a pi system, will be involved in resonance, and does contribute to full conjugation. I can draw a resonance contributor with the lone pair on this nitrogen that touches all of the atoms, but I don't need to use a lone pair on the nitrogen already involved in a pi bond. So the nitrogen with all single bonds, those lone pairs do contribute to the pi system. That's 2, 4, 6 total pi electrons. We've seen that several times already. That means that n equals 1, and imidazole is aromatic. We're finally ready to tackle the second rule. I've been avoiding it until now because the second rule is the hardest one to see in two-dimensional space. I'll remind you again that aromaticity is ultimately a measure of stability. A molecule will do anything it can to be as stable as possible. If it can be aromatic, it will. If it can avoid being anti-aromatic, it will. All it wants is to just be stable and live its life. With that in mind, let's look at cyclooctatetraene. Just looking at it, it's certainly cyclic, and it has a p orbital at every position. It is fully conjugated. If we count up the number of pi electrons, each pi bond contributes 2 electrons. That gives us a total of 8 pi electrons in cyclooctatetraene. Solving for n, that should give us 3 halves, which means cyclooctatetraene looks like it should be anti-aromatic. Do you think it wants to be anti-aromatic? No, it would really prefer to not be anti-aromatic. The smaller rings that we've seen so far have not been able to do anything about it. But when we have a larger ring, like size 8 or larger, we can do something about it. And cyclooctatetraene transforms into a puckered shape to avoid being anti-aromatic. By rotating into this puckered conformation, all the p orbitals are not fully aligned, are not fully parallel, and this molecule breaks full conjugation. Some of the p orbitals point vertically straight up and down, and other p orbitals are horizontally aligned. That means this molecule is not fully conjugated anymore. Normally, you'd tell me that's a bad thing. We would like to be fully conjugated so we can have full aromaticity. But doing so would make cyclooctatetraene anti-aromatic. So cyclooctatetraene instead chooses to adopt this non-planar puckered conformation so that it can become non-aromatic, which will ultimately be more stable for this molecule. And that's our final second rule. The molecule must be planar. For all small rings, they will have to be planar. It's only the larger rings that can break out of planarity if it's more stable to do so. Let's look at our last example, the 10-annulene. It's cyclic. It looks on two-dimensional space like it's planar, and it is fully conjugated. If we count up the pi electrons, 2, 4, 6, 8, 10 total pi electrons. We've solved for that before. That gives us n equals 2. So this one looks like it should be aromatic, but it's not. What I want you to focus on is these positions right in the middle. With this trans orientation around this double bond, that puts these 2 hydrogens pointed directly at each other in the center of this ring. They are not allowed to occupy the same volume of space. And so what that means is that those 2 hydrogens will end up puckering the molecule a little bit. One will go down, one will go up, and unfortunately that's going to break conjugation for this molecule. So this molecule also is non-aromatic because it ultimately makes it more stable. You would think being aromatic should be more stable, but not if those 2 hydrogens have to have their electrons occupying the same volume of space. You can't do that. These 4 rules work together like a filter. Break one of the first 3, we can't even get to the 4th. Break one of the first 3, automatically non-aromatic. Past the first 3, we can apply the 4th rule. If we also pass the 4th rule, the molecule is aromatic, but if we break the 4th rule, the molecule is anti-aromatic. Aromaticity is one of those concepts that looks intimidating until you break it down into these 4 simple rules. You got this. Let's keep going.
Thanks for training with us today, Ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.